Hey folks, Mrs. White here, hoping that you all are doing good, chilling out, relaxing at home, ready to do some stats work. We are moving right along in chapter 11. We're actually only going to be covering 4 sections, so today we're going to cover section 3. We're going to be looking at 2 means again, just like we did in section 11 too, but instead of them being dependent or matched pairs, we're going to be dealing with independents today. And it seems like it might be easier, but there's actually a little bit more to it. So we'll start off by looking at a hypothesis test, just kind of reviewing some older stuff. Then when we get started on this section, we're going to learn a little bit about Welch's approximation. Because if you remember way back when we started looking at sample means, we learned that not everything always works out well for them. We can't use the normal curve, we have to use the t-curve, or student's t-chart if you remember. Well, same things apply here, but we use Welch's approximation. So we'll talk about that and the notation for it. Then we'll hop into hypothesis testing. We'll talk about degrees of freedom and how we can use those to find our critical values. And then we'll talk about confidence interval. So if you found the sheet that is attached to this assignment on Google Classroom, it only has 2 examples. It has one of these and it has one of these. Your homework tonight, again, sheet is also or should also be attached to the Google Classroom, is 3 problems on page 554, numbers 1, 13, and 19. So let's get talking about some little review and we'll get going on some new stuff too. So looking at this problem, ATM withdrawals. According to Crown ATM Network, the mean, and this is important to read, I know we're dealing with means today, but we want to make sure we recognize that in a problem. The mean withdrawal is $67. So generally speaking, people pull out $67 from ATMs. Payees Incorporated manufactures an ATM that allows one to pay bills as well as withdraw money. So they can do 2 things at that ATM. It's maybe a little more convenient. A review of 40 withdrawals shows that the mean withdrawal is 73 from the payee's ATM machine. Do people withdraw more money from this ATM machine? So a layman would say, yeah, 73 is more than 67, but a statistician would say, all right, we need to hypothesis test that, okay? We need to see, is 73 actually statistically significantly larger than 67, or is it close enough that it doesn't really matter? So we would do a hypothesis test. Now, this is only one sample, which is important to remember. Okay, that's all we're dealing with here. So this is technically chapter 10. And if we're dealing with sample mean, we're looking at section 10.3. So let's write, just like it says here, our null and our alternative hypothesis for this. So the null, if we're dealing with one sample, is that there's no change, okay? So it's going to be that it equals whatever you started with. And our starting information was 67. Now, when I say it equals, we should be saying the mean, because we're dealing with a mean. But we're dealing with a sample mean, so we put our little X bar. So the mean of our sample mean. Our alternative is that the mean of our sample mean is going to be bigger than 67. And we already know that it is larger, but we're testing to see, is it statistically significantly larger? Okay, so there's our null and there's our alternative. Is this actually, even though that is 73, is that actually statistically larger than 67? So we would have to plug in a bunch of information, some of which they didn't give here. So they're just telling us, without having to plug it all in, suppose our p-value is 0.02, okay? So write a conclusion if we have a 0.05 level of significance. So we take our p-value. We want to see if it's less than our level of significance. And the answer here is yes, it is. That is a true inequality. So if this is true, if it actually is smaller, that means there is enough evidence to reject our null and accept our alternative. So if we were to write a conclusion for this, I would say something like, there is enough evidence at a 0.05 level of significance to say that the mean amount of money withdrawn from the payee's ATMs is larger than other ATMs. Okay, so they're statistically significant, there's evidence to show, and we want to make sure we include that level of significance. Okay, and hopefully that's familiar. We did a lot of stuff like that on our 3rd test that we finished just before school let out. All right, so let's get talking about 11.3. So here we're going to be looking at 2 means, and our samples are going to be independent. So an example of this could be, maybe we're looking at some sort of medicine. and it's supposed to make you get over your cold quicker. So you would have two groups, your experimental group, and you would have your control group that aren't receiving the medicine. Okay, now people in your experimental group do not dictate who is in the control group. You're not doing a married couple, you're not doing a family member, you're not doing like half of one person's body and the other half here, okay? So because this group is being chosen separate from this group, that would be an independent sample. And again, because we're dealing with two means, we're not going to look at what percent of these people it worked for. We'd have to do some sort of average. So we could say like we're looking at the average time frame until the person's feeling better. Okay, so now you can see, all right, we're looking at two means, and we'd have to be able to determine, okay, is this experimental, decreasing the amount of time it is till they get better, or is it, the same, okay? And that would be our null would be the same. So because we are comparing two different means, and we've already kind of seen that sometimes means are a little funky, that's why we had to have the t distribution. When we're comparing two means, we actually have to use Welch's T. And we're not going to spend a whole bunch of time talking about that, but what happens is if you're taking a sample, okay, from some sort of population, and you do not know the standard deviation of those populations, then you would use this calculation. And this is generally what we're going to be using as our test statistic. You do not need to write this down right now, but it's interesting to see how they're handling the two samples. So we're just going to talk about it really quickly. So if you think about our another t-score or our other z-scores, we always have a raw piece of data here. And we always subtract the average from it, right? And then we put it all over the standard deviation. That has been our test statistic that we've done over and over and over, and it looks a little different for each of the hypothesis tests. So here, since we have two samples, okay, and we're looking at the difference between the two means, we would take our first sample and our second sample, and not just our first and second sample, but remember, x bar means the mean. So we take our first mean of our first sample, the mean of our second sample, and subtract them, since we're doing a difference. Then we would take our original pieces and parts here, okay? And for hypothesis testing, this would be the null piece, potentially. Or it could be, if they give you the population means, you could use that. You'd find the difference there. Subtract those. So your raw data minus your means, dealing with two, over, and this is just like our standard deviations. Now this looks a mess. We'll talk about that notation in just 1 second, but this really is like this standard deviation plus this standard deviation, and it's all under the same square root. So raw data minus kind of your population piece all over those two standard deviations. Okay, so it's kind of interesting to see where our test statistic is going to come from. It's not like it's a normal t-score or a z-score. It's going to be Welch's T, and that's how we handle doing these calculations with two means that are independent. So to actually go through testing these is not horribly atrocious, okay? What we're going to do is a lot of the same stuff we've done in the past. So on that sheet that's attached to this lesson, you can see there's going to be 2 word problems, so there's not a lot going on as far as notes. We are going to cover one other side piece to put in your notes, but generally this is what we're doing. So in Science Lab Life Sciences 2 payload, 14 male rats were sent to space. Okay, so in this actual space lab, 14 male rats were sent to space. Upon their return, their red blood cell mass in milliliters of the rats was determined. So how many red blood cells they have within their blood. A control group of 14 male rats was held under the exact same conditions except for space flight as the space rats, and their red blood cell mass was also determined when the space rats returned. So same time frame, same other conditions. The only difference is space and not space. The project resulted in the data listed in Table 3. Does the evidence suggest that the flight animals have a different, okay, and that's an important word here, different red blood cell mass from the control animals at a 0.05 level of significance? So, first off, we're going to ask ourselves, how many samples are there? There's 2 samples. And what are we measuring here? We are measuring a mean, okay, because they're giving us some raw data. They also want us to know if generally speaking, right, if this is generally the same as this, we would find that with our average, okay? So we're going to test 4 things just like we did in the previous section. First things first, is it random? They did say that rats were sent into space. We can assume that yes, it was random, whether the ones that went or stayed, they were randomly chosen. Next is going to be independent or dependent. So did these rats in our space group dictate which rats had to stay? Probably not. It seems like they were just randomly chosen. So this would be independent. Next, we need to, just like we do with every mean, we need to see, is our sample size big enough? And is it also small enough? And I know that sounds silly, but that's really what we look at. So here we want to know, is our sample size greater than or equal to 30? And here, in each of these groups, there's actually only 14. So it is not right off the bat going to be big enough. So that means we're going to have to do 2 additional tests. We're going to have to look for outliers in a box and whisker plot, and we're going to have to look if there's a linear association in the normal plot. The last thing we're going to be looking for is that, is it too, we already know that it's not big enough, so it's probably not going to be too big either. Are both of these samples going to be less than or equal to 5% of the population? And clearly there's a lot more rats in the world than the 14 here and the 14 here. So that one definitely checks out. So before we get going, we're going to have to pull up our calculator, plug these 2 things in, and actually make our box and whisker plot and make our normal plot. All right, so in order to confirm, that our smaller sample is normal, we're going to have to construct a box and whisker plot, and we're going to have to construct our normal plot. So before we do either of those, we have to put our information into L1 and L2, and honestly, we have to do that for hypothesis testing anyway, so it's not a big deal. So we're going to edit. We're going to clear out what's already in here. And we'll go here, clear that one out, and we'll clear this one out. So I'm going to speed this up, and feel free to type your information for the rats that went to space, so the flight in L1, and then the control group in L2. All right, now that I've input everything into L1 and L2, I'm ready to make my box and whisker plot. So we're going to go into our stat plot option. So I'm going to do second stat plot. It's already on from my previous lesson, so I'm just going to enter to get on in there. I'm going to create a box and whisker plot with the potential of outliers, and I'm going to do it for each of the graphs because I'm not doing necessarily the difference of these right now. I'm going to have to test each one. So we'll start out by doing L1 to see if that is approximately normally distributed. And we will zoom 9. And that looks pretty linear, which is a good sign. So now I'll do the same graph. And I'm going to, let's see, go into stat plot 1. I'm going to go back to my normal plot. I'll make this L2, and then we will zoom 9 it. Now that one actually appears to have a little bit of a curve to it. Being that I know from the book that this is close to normal if you check the critical value in the back, it should be good to go. But it does seem to have kind of this underlying nonlinear pattern. It's almost like a cubic if you take a look. Like, it doesn't seem perfectly linear, but if we were to check it against the critical value, it would be fine. Our next thing is we need to check for, we need to check a box and whisker plot, for outliers. So we're going to go back in. We already have list 2 plugged in. So we'll just go over to box and whisker plot, press enter, and we'll look at L2. So everything's set up. We'll go zoom 9 for that one. It looks pretty symmetrical. So there's not like a huge skew and there's no outliers, so that's good. So go back into that same stat plot. And this time, instead of testing L2, I'll look at L1. So I'll go second 1 to get my L1. And we'll zoom 9 it just to make sure we're good to go. Yep, and again, no outliers there either. So that's good. I'm going to be able to do my hypothesis test and not worry about it. If there were outliers, then there would be an issue and I would not be able to hypothesis test it. So at this point, we can assume that our data, both sets, are generally normally distributed, and it follows the rest of the kind of prerequisites that we have to have. So it's random, it's independent, no outliers, it's approximately normal by looking at the plot being somewhat linear, and that's a little wrong right there. It should be that the sample size has to be less than 5%, not 50% of the sample. So all of those seem good to go. I'm ready to write my null and my alternative. So for the null, because we're looking at two independent events, I do not have to have the mean difference, okay? Even though I'm looking at if they are different or not, I can compare them as separate entities because they are independent. This is the big difference between independent and dependent means, okay? So here, I'm just going to say that the two means, so the mean from my first group, and we'll assume this is my first group, my flight group, if it is my null, it should be that it's exactly the same as the other one. Okay, the mu for my second. My alternative hypothesis is going to be that they are different. Okay, and if you remember, our terminology is different means that I would take my first one and it would just not equal my second. So it could be that it's a lot larger, it could be that it's a lot smaller. Either way, that's what I'm actually testing. My alpha, my level of significance, is 0.05. And then because this is a does not equal, that is not a great graph there, it means that I'm dealing with something that's two-tailed. So I'm going to have to kind of keep that in mind when I look at my classical method. So what happens next is we start crunching some stuff in our calculators. So you saw that large calculation, right, that we would have to do, Welchs T, to find our test statistic here. So instead of calculating that test statistic by hand, we're going to go right over and just do our p-value calculations. And from there, we can get our test statistic that we'll need in our classical. Okay? So hop to our, not computer, we're going to hop over to our calculator in just a second. Maybe before, you might want to put in your notes that we're going to go stats. Like always, we're going to go into test. And then this time, we're going to go down to option number 4, which is to sample t-test. Okay. Now, the reason why this is important is 2, because we're looking at 2 samples, and it's a t-test because we're dealing with the mean, okay? So when we were dealing with our matched pairs, right? When we were dealing with our dependent sample, we ran a different test because we were really only testing one column. We were just testing L3, which was the difference. Here, because we have 2 separate columns, L1 and L2, we need to choose this as an option. So let's go back to our calculator. We'll go stats. We're going to go over to tests. And we're going to go down to 4, to sample t-test. Now, we have data. If you have statistics, these are what you would need. You would need to get your sample mean, you would need your sample standard deviation, and your sample size. You would need that for both options before you were able to do anything. We do have our data here, so we're going to go data L1, L2 with a frequency of 1. We want them to test that they're not equal. And this is not pooled data. So pooled data is going to happen when you have a weighted average. That is not something that we're going to have to worry about right now. Actually, I don't think we're going to have to worry about it at all in this course. We're going to be dealing with non-pooled data, especially in Chapter 11. So don't worry about that. That's always going to be no for now. And then we're going to calculate. And you can see from here, we have our test statistic, which is going to be negative 1.4368. And we have our p-value, which is going to be 0.1627. Excuse me. So let's get our p-value down. We said that was going to be 0.1627. And over here we have our test statistic, okay, which is negative 1.4368. Oops, sorry about that. Let's do our p-value test because that's very quick and easy. we're going to take our p-value, we're going to ask ourselves if it's less than our alpha value, okay? And here it is not less, so there is not enough evidence to accept our alternative. We instead do not reject the null, which means we're kind of like accepting the null. For our classical method, we're going to figure out what's going on with our test statistic in relation to our t-curve, okay? So we're going to need to find the t-scores for 0.025. Remember, because our area is 0.05 and we're splitting it into two pieces, this t also has to be negative because it represents the left-handed side, okay? So as we take a look at finding these t-scores, we're still going to go to the back of the book, and we're going to go to, what is it, table 7, I think? Let me flip to it real quick. Yep, we're going to go to table 7. Okay, now as we're looking at table 7, you always need to write degrees of freedom. And what's important for you to know is that when we are doing two independent tests, you always take your lowest amount of degrees of freedom from your two samples. Now, our samples both were 14, so our degrees of freedom are going to be 13. But if you had two different sample sizes, for example, let's say we had a sample size of 20 and a sample size of 15, we would have to use 14 degrees of freedom. Okay, you always have to use your lowest because you're dealing with two samples. They might not be identical. So if I go to my table, my degrees of freedom are 13. I'm going to go over to 0.025, and I get that it is 2.160. So this side is going to be negative 2.160. And I should write it below, but I just don't have space. This side is going to be positive 2.160. So if we think about where is this negative 1 going to be, the negative 1 is going to be somewhere here, right? It's going to be below our mean, but it's going to be in the non-shaded area. So the question we ask ourselves is it in the shaded area? The answer is no. Again, that means there is not enough evidence to support changing. Okay, so instead we continue to kind of just accept the null. So our conclusion for this is that there is not enough evidence at a 0.05 level of significance to say that the two groups of mice's amount of red blood cells were different. Okay, so there's not enough evidence to say that they were different. And that's really hypothesis testing of two means, okay? It's a different keystroke. When we do our null and our alternative, we keep them as two separate samples because they are separate samples. They're independent, okay? Keep in mind, if your sample size is not greater than 30, you have to check your two graphs. So, the degrees of freedom seemed kind of willy-nilly, right? I said to you folks, if we're doing classical and we need to find our critical value, which is what these two numbers are, right? Our critical values, then you just use your lowest degrees of freedom. But that's not actually as rigorous of a calculation as we could do. So there is a way to calculate the best, I guess, calculation for degrees of freedom, and it would be doing this calculation that involves looking at your sample standard deviations for each, dividing them by the sample size, adding them, squaring them. This is a huge process. Some like hardcore statistical software programs will do this for you as far as calculating degrees of freedom, but when you're using your critical value, when you're calculating your critical values, which only some of you do, because in the past we've used that on tests as bonus points. It is on the quiz as a requirement. You do not have to do this calculation. I just wanted to kind of share that value with you. It's what some, heavy-duty computer programs might do, and that's why you might at some point get different calculations if you're not just using a table in the back of the book, okay? So our last piece for this section is doing our confidence interval. And again, we're looking at two means, and it's not just any rando two means. It is that they are two means and they are independent of each other. And we already kind of assumed or calculated or figured out that they were independent because we're using the previous example. Okay, so we're using that same table that involved the red blood cell count for mice that either went into space or stayed on land. So our keystrokes for this, again, I don't care about you using the actual formula. That's not important to me at this point in the year. You're going to go back into stats. You're going to go back into tests. And from there, you're going to go to option 0, which is 2 samp, and then it is T, but instead of test, it's interval, or just int. So again, we have the 2 because we're dealing with 2 samples. We use samp because it's a sample, and we're using the T because it's a mean, and int because we need the interval, okay? Remember when we did dependent, okay, we just did our normal T interval because we were really only testing our third column, our L3. Here we have those 2 separate samples, right, because they're independent, so we need to make sure to choose this option. So let's go over to that calculator. We'll clear her out. We're going to go back to stat, over to tests, down to 2 samp. We don't want z int, we want t int, right? Because we're dealing with means. So 2 sample t interval, okay? Press enter. We still have our data plugged into L1 and L2. If we had stats, we would go over here. We want a frequency of 1. And we do need a confidence interval of, it says over here, 95. So I'm going to type that in, 0.95. It is not pooled data, and we are going to calculate. And we get that our interval is going to be negative 1.335 to 0.23655. So we'll write that interval on in here. So parentheses, negative 1.335, comma, 0.23655. And if we were to interpret it, it doesn't ask you to, but we could. So let's take a look. We would say something like, we are 95% confident that the mean difference, okay, because we're still looking at differences between these two, that the mean difference between red blood cell count in animals that travel to space and the animals that stayed on Earth is between, and we would use those 2 numbers. Ooh, that's fun. Negative 1.335 milliliters and 0.23655 milliliters, okay? Because again, these are both a measurement. Since we're talking about average, it's not a percentage point, they're both milliliters, okay? So we're 95% confident that the mean difference between red blood cell mass of animals that went to space and those that stayed on Earth is between negative 1.335 milliliters or 0.23655 milliliters. The negative here means that it's less. The positive here means that it would be higher, okay? So it's going to be going down by this much or up by this much, okay? It's kind of like the give or take. That pretty much ties up section 11.3. When we check out the next lesson, it's going to be 11.4. That is looking at standard deviations. And if you've already previewed your chapter 11 quiz, you can see on there that there is a problem about standard deviations. So you do have to make sure you're paying attention to that for sure. Okay. If you haven't already printed out that chapter 11 quiz, feel free to print it out. It is a separate assignment under the chapter 11 materials. If you don't have a printer, don't stress out. Just make sure you label all of the pieces and parts for numbers 1 through 5 on that quiz. Okay. We are going to have a day where I will go over some of the homework problems. I can maybe make myself live. We can figure out what we want to do next week as kind of like what we would have in class, which is a work day, okay? A day for you to have some time, extra time to reach out to me if you need to. Then we're going to be reviewing for our test the following class, and then taking a test either right after break, or if you're planning on staying at home, maybe that week you plan to take the test without taking your April break and take your April break from math class the following week. I'm open to either idea. I don't mind doing it on an individual basis. Okay, so if you are like, wow, I'd really like to just take care of that, we're not doing anything, great. If you're like, you know what, I'll take that week off just like everyone else, and I'll come back to it the following week, that's fine too, okay? So either you'll have your week when it's supposed to be or not. If that's confusing to you, we'll revisit it next week when we do our review for the test. All right, folks, if you have any questions, please, please, please attend our 4 to 5 p.m. office hours tomorrow. See you then. Bye.